Hello.
Hello, Assalamu alaikum.
Ahmed, can you hear us?
Yes.
Okay. They're coming.
I'm not the first presenter. I think I'm the third.
Sorry, Dr. Ahmed?
I'm not the first presenter. I will be
No,
the
no, no,
third.
no problem. I just want to check the mics are working fine with us or no.
It's okay. Alhamdulillah.
Yo, thank you so much.
Online. Hello. Hello.
Tell them paper number.
أهلا. أيوه. Oh,
Dr. Puneet have the experience with that.
okay. Yeah, okay, thank you. Okay, we are in session 3. Okay. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome everyone for this last session, which is packed with 4 interesting papers. The first paper, ID number 144, entitled Machine Learning Applications in Predictive Fetal Health Assessment and Early Intervention, by Saurav Kumar Ship and others. I'm not sure if they are presenting online. If you are presenting online, please let me know. Okay. Okay, so until the first paper author comes, let's, Athir, are you ready?
Hi, yes, I'm ready.
Okay, Athir. So let's start with your paper, Stacked LSTM GRU with double attention model for Arabic aspect-based sentiment analysis.
Yes,
Athir,
sure.
the floor is yours, and please go ahead.
Okay, thank you. But I need to share my presentation. Okay, just a minute, please. Okay, can you see my screen?
See your screen.
Okay. Bismillah ar-Rahman ar-Rahim. Good afternoon, everyone, and thank you for being here today. I am Athir Al-Ghamdi, and today I'll be presenting my research paper, Stacked LSTM GRU with Double Attention, a module for Arabic aspect-based sentiment analysis. These are the outlines that we will cover today, inshallah. To begin with, the widespread adoption of social media platforms and the growth of e-commerce have increased online engagement. People now share their opinions, experiences, and feedback more frequently than ever before. And this had led to the availability of huge amounts of sentiment data, not only on social media, but also from other sources like news websites, and articles, and personal blogs, and so on. These developments present valuable opportunities for sentiment analysis, which involves analyzing and extracting meaningful insights from this sentiment data. And sentiment represents opinions, feelings, and emotions, and they can generally be classified into 3 categories: positive, neutral, and negative. Okay, sentiment analysis can be done at 3 main levels: document, sentence, and aspect level. At the document level, the sentiment of the entire document is classified as positive, negative, or neutral. And at the sentence level, the focus here is on determining the sentiment polarity of each sentence. However, our focus in the paper is on the aspect level, which takes a more detailed approach. Here in the aspect level, we classify the sentiment associated with each aspect within a sentence. For example, in the sentence المنتجع جميل ولكن الخدمة سيئة, using sentence level will not be accurate, as it's going to classify the whole review as either positive or negative, which is not correct. On the other hand, the aspect level will have the ability to classify the sentiment toward المنتجع as positive, while the sentiment toward الخدمة as negative. Okay, aspect-based sentiment analysis involves 3 key tasks. The first task is aspect category identification. And here we identify the aspect being discussed. For example, in the same previous sentence, المنتجع جميل ولكن الخدمة سيئة, here the aspects are المنتجع and الخدمة. The second task is opinion target expression extraction, which focuses on extracting the specific words expressing opinions about the aspects, such as the word جميل for المنتجع and سيئة for الخدمة. And finally, the third task, which is the focus of this work, is aspect sentiment classification. And here we classify the sentiment polarity for each aspect, such as positive for المنتجع and negative for الخدمة. Okay, now moving on to introduce some important techniques that are used in our model. We will start by word embedding. Word embedding is a fundamental component of natural language processing. It represents words as numerical vectors, and there are 2 types of embeddings. It can be non-contextualized, and here the vectors remain static regardless of the context, or it can be contextualized, and here we assign vectors based on the context. And to produce the contextualized embedding, we can use transformers. For the contextualized embedding, it's useful especially for cases where the meaning of the word change depending on the context. For example, the word right, it has 2 different meanings, more than 2 meanings, but here, for example, we can have the first meaning for direction, such as when we say turn right at the next street, while in the second sentence, she fought for her right, it gives a legal context. The second technique is the attention mechanism. And in a human perspective, attention involves focusing on important elements while ignoring others. And the same concept goes for machine learning. The attention mechanism enables neural networks to focus on specific parts of an input sequence. And this is done by assigning weights to different parts of the sequence based on its importance in the context. For example, here in the sentence, the view of the hotel is amazing, but the service is slow. The attention mechanism can help the model to prioritize the most relevant words by focusing on amazing when analyzing the aspect view, and on slow when analyzing the aspect service. This helps in having more accurate sentiment classification. Okay, the motivation for this work arises from several key factors. First, the Arabic language holds significant importance, ranking among the top 4 languages on the internet. And furthermore, a huge amount of available Arabic online content presents a valuable resource. Second, there is a growing need for sentiment analysis systems, as they are important for many applications. Third, sentiment analysis at the document level and sentence level usually fail to capture the sentiment tied to specific aspects, and this highlights the need for stronger aspect level capabilities. And finally, while Arabic is a widely used language, there is still limited research focusing on aspect-based sentiment analysis, which creates a significant gap for this work aims to address. Okay, now here we move on to the literature review summary. We present previous works that focus on the aspect sentiment classification task in Arabic language. And the table here summarizes these studies. For each model, we represent its encoder layer and whether it's hybrid or not, and the embedding layer and whether it's transformer based or not, whether the attention mechanism is used, and if it's multi-layer or single layer, and finally the data set used and the model accuracy. And as we can see, two works here employed hybrid deep learning models, but they both didn't use transformer embeddings, and only one of them benefited from integrating multi-layer attention. And on the other hand, there were only two models that used transformer embedding, but did not have a hybrid deep learning model for the encoder layer, nor a multi-layer attention mechanism. So as far as we know, after reviewing the existing aspect-based sentiment analysis literature, it has been believed that existing Arabic works on the aspect sentiment classification task lack a comprehensive model that effectively integrates transformer-based language model, hybrid deep learning networks, and multi-layer attention mechanism. Okay, compared to existing works, our proposed model contributes to the field of Arabic sentiment analysis by introducing an aspect-based sentiment analysis model that integrates hybrid deep learning architecture by stacking LSTM and GRU in the encoder layer. It also integrates a double attention mechanism layer to refine focus on relevant text features at multiple stages. And additionally, the transformer-based pre-trained embedding is effectively combined with double attention layers and hybrid LSTM GRU structure, improving the aspect level sentiment analysis. The methodology followed in our model consists of 6 main phases, and now we will go through them one by one. Okay, the first phase is dataset selection. We used the Arabic Hotel Reviews dataset to train and evaluate the proposed model. The dataset is a benchmark dataset specifically designed for Arabic aspect-based sentiment analysis task. And as shown here in the image, the dataset contains reviews written in different Arabic dialects. And each review in the dataset includes aspect and corresponding sentiment polarities. And the aspect categories include hotels and services as shown in the picture, and other aspects such as rooms, facilities, locations, and more. And for each aspect, the sentiment is categorized as positive, negative, or neutral. Okay, moving on to the next phase, which is text preprocessing. Text preprocessing is an important step as it helps in enhancing the quality of the data, leading to the quality of the data to improve accuracy. And these are the preprocessing steps that we applied: data cleaning, normalization, tokenization, and padding. Okay, now we move on to the model implementation. The proposed model consists of 3 main layers as shown in the figure. And these include the Arabic BERT-based pre-trained language model as the embedding layer, stacked LSTM GRU encoder layer, and the double attention layers. And a comparative analysis was conducted for these 3 main layers to identify the best performing architecture. The first layer to discuss is the embedding layer. Okay, as mentioned previously, there are 2 types of word embedding: contextualized and non-contextualized. BERT is one of the most powerful contextualized word embedding techniques. It's a transformer that provides a deep bidirectional pre-training for language representation, and it was developed by Google in 2018. And to select the optimal choice for embedding Arabic text, we tested the model using different Arabic BERT-based language. And in the embedding layer, we leverage BERT's ability to handle pairs of sentences by inputting the entire review as a single sentence and treating the aspect word as an auxiliary sentence. The second main layer of the model is the encoder layer. And in our experiments for the encoder layer, we use different types of RNNs, such as LSTM and GRU and their bidirectional versions. LSTM is effective at capturing long-term dependencies, while GRU is useful for short-term and long-term dependencies using simpler architectural design. And in the stacked arrangement, the input embeddings are first processed by the LSTM layer, and once it's done, its output will be passed to GRU. And by stacking LSTM and GRU, the model becomes able to handle the sequential nature of the Arabic text more effectively and can learn more complex relationships within the sequence. Okay, now moving on to the third main layer of the model, which is the double attention layer. Okay, to find the best configuration for the attention layer block, we conducted experiments using 2 types of attention: single head and multi-head attention. In single head attention, each word in the sequence is assigned an attention score that weights its representation. And on the other hand, multi-head attention computes multiple attention scores in parallel across different heads. The attention score for a word is calculated using the additive attention equation. And having this double attention layers enables the module to refine its focus on the most relevant words to make sure that accurate representation of the sentiment polarity is achieved. Okay, the output of the attention layer is then fed into a dense layer with a RealU activation that helps in further refining and transforming the learned features. RealU is used to add nonlinearity to the network, enabling it to recognize and learn complex patterns and relationships in the data. And then finally, a softmax function is used to classify the sentiment of each aspect as positive, negative, or neutral. These are the hyperparameters that we used. It's summarized in this table. And here, these are the metrics that are used to evaluate the model. We used accuracy, F1 score, precision, and recall. Okay, here now moving on to the model evaluation. This table shows the performance of the model with different Arabic BERT-based pre-trained language models. And as we can see, using AraBERT version 2 based, achieved the highest accuracy. And then here, this table presents the results of using different R and N techniques for the encoder layer. First, we tested the model using only one layer of deep learning model, as shown in the first 4 rows. Then we stacked different combinations using LSTM GRU and their bidirectional versions. And the best performance was achieved by using a stacked configuration of LSTM GRU. And then here, finally, for the double attention, the table here shows the results of different attention layer configurations. And as seen here, the best performance was achieved with double attention using a single head configuration. Okay, this example here shows how the model correctly predicted different aspects polarities within a single review text. As we can see here, خدمة سيئة, فندق رائع جميل جدا. We have 2 different aspects. We have خدمة and we have فندق, and each with different polarity. And the model had the ability to classify them correctly. And to further illustrate the strength of the 2-layer attention mechanism, we provide some examples that highlight the mechanism's ability enhancing sentiment prediction capabilities. After studying and analyzing the results, we found that the 2-layer attention model distribute attention more effectively by focusing on contextually relevant words and minimizing it on irrelevant words. As shown here in the example, ولا يوجد أقل أصول الضيافة والترحيب حتى المياه أو عصير النزلاء فور وصولهم. The words لا وأقل, which are the key indicators of negative sentiments, they both received greater attention with double attention layers. And this focus allows the model to correctly predict the negative polarity of the aspect of الضيافة والترحيب. On the other hand, the single attention layer fails to capture the importance of these words, leading to an incorrect positive prediction. And this is another example to show the same thing. السلبيات, حجم الغرفة, النظافة, وجودة التكييف. We can see that the السلبيات in the double attention layer receives higher attention than using one attention layer. And using one attention layer, it predicted wrong polarity. It predicted it as neutral, although it is negative. And this was correctly classified using the double attention layer. Okay, this table here compares the proposed model performance against the baseline model and the state-of-the-art Arabic models. The baseline model is an SVM-based classifier that was trained using Ngram's features. And as shown in the table, compared to the baseline model, our proposed model achieves a remarkable 18.2% accuracy improvement. And furthermore, it also surpasses the best performing existing state-of-the-art Arabic model by 3.90%, reaching an accuracy of 94.71. Okay, to conclude, the importance of Arabic aspect-based sentiment analysis is underscored by the growing amount of Arabic sentiment data generated from social media and commercial platforms. Our contribution to this field is to develop an Arabic aspect-based sentiment analysis model that incorporates transformer-based pre-trained language model for word embedding, stacked deep learning networks for capturing contextual dependencies, and a multi-attention layer.
Follow that, but it also basically prototyping in the project. The actual functioning, functional unit is in the project.
Excuse me, sorry. Can you mute yourself, please? Thank you. And the third is a multi-attention layer mechanism for refined sentiment analysis. This integration outperformed the state-of-the-art models by 3.9 with an accuracy of 94.71%. And this model focuses on the Arabic text, improving the analysis of aspect level. Okay, for future work, there are three key areas to focus on to enhance the proposed model. First, class imbalance handling, and this can be done through techniques like data augmentation, oversampling, and class balancing to improve the model's accuracy. Second, the collection and labeling of larger and more diverse data set to enhance the model's ability to generalize across different contexts. And third, the integration of emoji analysis using pre-trained emoji embeddings such as Emoji2Vec. It might enable the model to capture additional sentiment through emojis. Thank you so much for your attention, and any questions? Hello? Can you hear me?
Can we change the order of the stacked middle instead of starting for LSTM and GRU? We can swap these two models in your model?
Yes, I did try that, changing the order, but I didn't receive a higher accuracy than what I achieved with the LSTM then having GRU.
Type, what is the effect of stacking mini model in order to get better result, of course, on the performance?
What do you mean by mini model? Do you mean without using the bidirectional versions?
يعني you are using two stacked middle LSTM and GRU beside double attention model.
Sure.
Yeah, so stacking is all this model in to find the solution has any effect on the performance of your system?
Yeah, the stacking, yeah, we tried, let me just share the presentation again. We tried evaluating the model without the stacking using only one of them, only, for example, only LSTM or only GRU. And we also, just a minute, please. Yes, here. As you can see, we tried only one layer, LSTM and GRU, and only one layer of BiLSTM or BiGRU, but they all gave less accuracy than what we achieved with LSTM and GRU together.
Why your model gives a better result?
Using LSTM and GRU. The stacking helps us to benefit from the advantages of both LSTM and GRU.
Yeah. But there is a price for that, for better performance. There is a price, I guess.
You mean maybe having longer time for execution and so on?
Yeah, something like for performance.
Yeah, that's true. But we were focusing on achieving the highest accuracy. We can work on these things for in future work. That's true.
Okay, thank you, Athir.
Thank you. Thanks a lot. Thank you.
Thank you very much, Athir. I think we need to move to the next speaker. For the first paper, are you available for machine learning applications and predictive fetal health assessment and early intervention?
Yes, ma'am.
Please, the floor is yours, and you have 15 minutes for the presentation. You can start. Number 144. Yes. Machine learning applications and predictive fetal health. I think the author, Durjoy Roy. Are you available?
Hello, ma'am.
Yes.
My screen is
Please
visible, ma'am.
share your screen, please.
My screen is visible, ma'am.
No. Okay. Make
Hello,
host.
ma'am. Right now, my screen is visible.
Yes. Okay. Thank you. You can start sharing your screen now.
Hello, ma'am.
Yes, I think you can share your screen. We don't see your
Yes.
screen, but you can share it.
Ma'am, my screen is visible.
No. Click share screen in your Zoom, and it should appear to us. Stop sharing. Okay. Share your screen again, Durjoy. Okay. Now it's appearing. Just 1 minute. Yes, we can see it now. You can start.
Hello, everyone. I am Durjoy Dipto. Welcome to my presentation session. This session about an machine learning application in predictive fetal health assessment and early interventions. Throughout this study, we aim to contribute to medical advancement by improving prediction accuracy and assist doctor to diagnosis making. Let's begin our discussion on how technology can enhance fetal healthcare. Pharmacy-related applications can lead to risks if not diagnosed early. Traditional medical examinations help, but they may not always detect issues in time. Machine learning offers a way to analyze complex fetal data quickly and accurately. It can recognize patterns in fetal health rate, movements, and construction, helping doctors take timely action. Current method rely heavily on manual analysis, which can sometimes lead to human errors. By using automated model, we can reduce the risk significantly. In our study, we explore how machine learning can predict fetal health condition and assess in early intervention strategies. These research can help improve mental care and ensure a safer pharmacy for both mother and the babies. Our research focus on three key objectives. Developing a advanced predictive model, we aim to create a machine learning system that can assess fetal health more accurately. Improving early diagnosis, many fetal health problems are diagnosis late, leading to complications. We seek to enhance early detection. Comparing different machine learning models, we test multiple models to find the most accurate and reliable one. We hope our finding will assist doctors in making informed diagnosis and reduce the risks of undetected complication. Previous literature review. Previous studies have explored machine learning in medical diagnosis. Many researchers have used algorithms like SVM and random forest to predict fatal condition. However, most exciting models have limitations such as imbalanced datasets, low accuracy, and lack of real-world application. Some research focus on fetal heart rate analysis, but it does not always consider other critical factors like uh, construction and fetal movements. To bridge these gaps, we review past studies, analyze their strength and weakness, and build on their work to improve accuracy and reliability. By using better pre-processing techniques and advanced model, our study enhanced previous research in fetal health prediction. There are several gaps in current research that we aim to address. Low prediction accuracies. Some models struggle to differentiate between similar fetal conditions. Data limitation. Many studies rely on a small dataset, reducing the model's ability to generalize. Handling missing data. Many studies ignoring missing values instead of properly inputting them. Our contribution include using advanced pre-processing techniques to handle missing value and imbalance data, testing multiple models and selecting the best performing one for fetal health prediction, proving a detailed comparisons of various machine learning approaches. Now, methodology. We develop a machine learning based predictive model for fetal health assessment. The model takes input uh, features like fetal heart rate and fetal movements to classify health status. It catalogs a fetal condition into normal and suspect and pathological based on expert obstruction levels. Our methodology includes data pre-processing, model selection, training, evaluation, and final confirmation of different machine learning techniques. These systems approach ensure that we obtain the most accurate and reliable result. We used a dataset from Kaggle containing 2,126 records of fetal health assessment based on CTG exam. This dataset includes critical medical features such as fetal health rate and untrained construction and fetal movements. It was labeled by obstructions into three categories: normal, suspects, and pathological, requiring the datasets provides a strong foundation for training and testing our machine learning model. To ensure our model works efficiently, we perform several pre-processing steps. Handling missing values, uh, we check missing data and use techniques in like mean, medium, and mood implications. Data normalization and scaling. We apply standard and minimum to maximum scaling to bridging all features to a uniform scale, solving class imbalance. And since some fatal condition are less, we use SMOTE uh, to balance two dataset. The feature selection, we use correction analysis and principal component analysis to select the most important features. Data splitting. The dataset was divided into 70% training, 20% validation, and 10% testing sets for better model evaluation. We used various performance metrics to assess model effectiveness, accuracy, measuring overall to predictions and precision, ensuring that positive prediction to truly positive, and recall measuring how many actual positive carries were accurately predicted. If F1 score, balancing precisions and recall for better assessment, and ROC curves and AUC score shows well how well the model between different fetal conditions. This matrix helps us determine the best model for predicting fetal health. We tested five different machine learning models. Logistic regression, a simple but effective classification model. Support vector machines, SVM, works well with medical data. Random forest using multiple decision trees for better accuracy. Key nearest rebrons, KNN, a distance-based classifier, and XGBoost, a powerful boosting algorithm with high accuracy. Each model was trained and evaluated to determine the best performing model. Logistic regression is a simple model that works well for linear patterns but struggles with complex ones. This confusion matrix shows moderate accuracy but misclassification between suspect and pathological cases. The ROC curve indicates limit separation between pathologic and making it less effective for fatal health prediction. While easy to interpret, it lacked the complexity needed for high accuracy in medical datasets. SVM is powerful model that finds the best boundary between classes. The confusion matrix shows better performance than logistic regression, especially for normal cases. The ROC curve indicates an improved AUC score, meaning better class separations. Thought accurate SVM is computationally expensive and lower to train. Random forest combines multiple decision trees, improving classification accuracy. This confusion matrix shows better result and reducing misclassification. The ROC curve confirms a strong performance with a high AUC score. This model balances accuracy and making it a strong candidate for fatal health prediction. KNN classifications based on nearby data points but struggle with high medical data. This confusion matrix shows good performance for normal cases but errors in distinguishing suspect and pathological cases. The ROC separation ROC curves has a lower AUC score indicating weaker separation. KNN is simpler but less effective due to high misclassification rates and computational cost. XGBoost is advanced boosting algorithm and that provides the highest accuracy all models. This confusion matrix shows minimal misclassification, making the most reliable. The ROC curves has the highest AUC score, providing its superior class destination. Through computationally damaging XGBoost is the best choice for fatal health prediction. XGBoost performed best at achieving the highest accuracy and AUC score. Random Forest provided a strong performance balancing and precision and recall. SVM performed well but required more computation. KN had a lowest accuracy with complex cases. Logistic regression served as a but its simple approach was. Overall, XGBoost is the most effective model followed by Random Forest and SVM. Some challenges we face: handling imbalanced data to avoid based prediction, ensuring the model works well with new unseen data, reducing false positive and false negative prediction. In future, we plan to use larger and more diverse dataset, apply deep learning techniques for improved accuracy, collaborates with medical and for real world application. In conclusion, our study shows that machine learning can effectively predict fatal health conditions by improving data pre-processing and using advanced model. We achieve high accuracy. This research can help doctors make better decisions and improve material care. Future work will focus on integrating this model into real-world healthcare system. Here is our references that supported our research. Thank you, sir, for your attention. Any questions?
Thank you very much. Time for questions. Anyone have any questions from the online participants? Anyone has any question?
Okay, thank you for your nice presentation. I have only one question. What is the purpose of scaling you have made in your model? Is this to give a weight for one features more the other, or what is the purpose exactly? Do you hear me?
Do you hear us?
Sir, I cannot understand, sir.
My question is, you in your model made the scaling. What is the purpose of the scaling in the model? Is it to give weight for a features higher than the other or less than the other, or what is the purpose exactly?
Sir, we applied standardization for minimum and maximum scaling to bring all features to uniform scale, sir.
Okay, thank you.
Would like to introduce okay, thank you very much, Durjoy. And now we move to the third paper. Ahmed Harbawi, are
Thank
you
you, ma'am.
available?
Yes.
Okay. So we move to Ahmed Harbawi's paper, Forecasting Prices of Strategic Food Products, Time Series Models in the Context of Post-Crisis Market Disruption. Please go ahead, Ahmed. The floor is yours.
Just try to share our slide.
Okay, I will assign you as a host. How can I close the Ahmed. The previous one was this, but I also am unable to remove.
Can you see my screen?
Thank you. You can start now.
Okay. السلام عليكم ورحمة الله تعالى وبركاته. It's an honor to be here with you. I'm Dr. Ahmed Harbawi from FSIT, King Abdulaziz University. And I will present my paper, Forecasting Prices for Strategic Food Product, Time Series Model in the Context of Post-Crisis Market. Okay, let's start by, before we divide into the detail, let's provide an overview of our discussion today. We start with a study of weight price trends, literature review. Can you hear me?
English practice.
Please, if you
এবার আমার লাগে ছোট ছোট দেখে এবার আমি বলছি যে স্ক্রিন দিয়ে হয়তো প্রশ্ন করছে এই স্ক্রিন দিয়ে বাইরে দিচ্ছি
Roy,
আচ্ছা
Roy, please.
ল্যাঙ্গুয়েজে দিন আমার আমি ঢং খাই
Okay. So before we divide into detail, let's provide an overview of our discussion. We start with the study of weight, prices, trends, lecture review. We present after that our data set description, our methodology, and we conclude with the experimental results and the future work. Food security is one of the most pressing challenges of our time, and smart cities must integrate advanced forecasting techniques and tools to ensure stable and resilient food supply chain. The prices of raw material, especially wheat, have become more unstable due to the recent global crisis. The COVID-19 pandemic and the Russia-Ukraine war have caused major disruption, impacting food market around the world. This is particularly important because Russia and Ukraine together make up 28 of the global wheat export. So any interruption in their production or trade affect the whole world. To address these challenges, our research focus on identifying an accurate forecasting model for wheat prices in post-crisis period. By using predictive analytics, we can provide policymaker, urban planner, and supply chain manager with tools they need to mitigate risk and to enhance food security in smart cities. Let's move on the specific objective of this study. Our goal is threefold. The first is to compare the performance of ARIMA and the LSTM models in forecasting wheat prices. Next, we aim to estimate wheat prices for the next 12 months following the crisis. Finally, we will provide decision-making tools that can assist policymakers in navigating this price fluctuation. This objective will guide our analysis and help ensure that the results are relevant for food security planners. Now let's explore why this study is so important. We are currently in post-crisis period that is expected to last for several years, and accurate price forecasting is more critical than ever. Despite advanced deep learning, classical forecasting models are still widely used. These highlight the need to evaluate both approaches in the context of our studies. Additionally, with wheat prices being influenced by volatility, seasonality, and unclear stability, identifying the best model to forecast this fluctuation will be key to supporting informed decision-making in both policy and planning. Let's now look at the wheat price trend for the last 10 years. As shown in the figure, price increased during key crises. We started with 2040 with Russia-Ukraine conflict for Al-Qarm annexation. 2020 for the COVID-19 pandemic, and 2022 for the Russia-Ukraine war. You can see from the figure, we can see that between 2014 and 2020, we have a relatively stable data. But after and the COVID-19 here in this period, after the COVID-19 pandemic and the start of the war, it was much more price fluctuation. Right now, we are in the post-crisis here in 24, 25, and the start of the war. Here was much more a price fluctuation. Right now, we are. So this makes it important to understand if in this new period, price change are more affected by the crisis or by a regular pattern. So we are not sure about the stability of this period. It is very difficult to predict when prices will return to their stability. Let's start comparing with using the literature review. For first model, it's ARIMA model. ARIMA is successfully and widely used for financial forecasting, stock prices, sale and demand forecasting, product sales, forecasting price for commodity and essential food product, especially this product. Several studies confirm ARIMA reliability you are here, we have here two studies. In our paper, we have many others paper and recent paper. Several studies confirm ARIMA reliability in short-term price estimation and predictable seasonal pattern. For the second model, LSTM is deep learning model suited for non-linear time series forecasting. Studies show LSTM outperforming other models in capturing price variation. Use it effectively for agricultural commodity forecasting, including wheat. Let's compare now ARIMA with LSTM based on our literature review. For ARIMA, ARIMA especially capture seasonality. It's suited for linear trends and easy to interpret, but struggles with high volatility. For LSTM, capture complex pattern, better but require more data. Some studies favor ARIMA, while others show LSTM superiority. Since 2023, this post-crisis period has been marked by unpredictable price patterns. Which model is better for the post-crisis period? Identifying the best model will help policymakers and farmers estimate wheat prices and make informed decisions. Let's move on now for our dataset description. We use dataset sourced from Chicago Board of Trade. This board is recognized for providing accurate and up-to-date market prices. CBOT is considered a reliable barometer for global wheat prices overall the world. We cover from January 10 years, from January 2040 to October 2024, and we divide our data set to two sets, 80% for training and 20% for testing. And we use the monthly prices in US dollar. Now let's focus in our methodology. We compare two models. The first is ARIMA. It's a classical statistical model. And the second is the deep learning model, which is a long short-term memory LSTM. We start first by dividing our data to two sets. And in LSTM, we use four layers: input layer, LSTM layer, dropout, and dense output layer. For ARIMA, we use to estimate our parameters with the autoregressive P and parameter D and Q. Calculate models performance indicator, and then compare the model performance to choose or to select the most suitable on the most accurate model for price estimation. Our estimation and our price prediction is done for 1 year during 12 months. And we use for evaluation many errors as MSE and MAE and others. For ARIMA models, for the first model, we use ARIMA model, but we use a special variant of these ARIMA models to include seasonal trends. So we start our algorithm with loading the price, wheat price, and forecasted wheat price. We split our data, and after that, we estimate or we use the parameter to order parameter with P, D, and Q for ARIMA, and the seasonal order like cycle, past period, and correction for seasonal order parameters. After fitting our model to data set, we run the prediction and we calculate the error matrix to compare with the LSTM. For LSTM model, we use many layers: input, hidden layer with 450 neurons, ReLU as activation function, dropout, dense, and output as output layers. A trend with 4 epochs and patch size of 16, optimized with ADAM optimizer. So our algorithm starts with historical weight prices. The output will be the predicted price for the next 12 months. After dividing our data to two sets, we build and train model, and we estimate many parameters in input layer, hidden layer, output layer, and compile a model. We use mean square error in this algorithm, but we use all others errors. And the optimizer is after fitting our model, we will evaluate the model with the 4 errors. Our experimental setup will divide data in 2 parts. The first part for 10 years from 2014 to 2023. and the testing part for the next 12 months for 2023 to 2024 to predict wheat prices in post-crisis context. Let's move to the result with ARIMA performance. As we can see here, you have the 4 errors, and according to this graph, you can show there is a gap between the actual and the prediction of ARIMA, and we have an MSE of 21,399 and a percentage of 23 as error, 23%. And accuracy with 77% accurate. For LSTM now performance, we show that LSTM is more stable and trend to predict the trend of the wheat prices. And we can see we have a minimal error with 600 for MSE and a percentage of 2.5. So we can obtain accuracy of 97.5%. Let's compare now the two models. If we have ARIMA prediction diverge significantly over time, LSTM maintains accuracy through the forecast. And we can see the big difference between errors and the accuracy between these two models. LSTM better handles volatility in post-crisis conditions, and we can see the cumulative error for LSTM and ARIMA may diverge in 12 months. It's very big in the last month. As discussion of our finding, LSTM outperformed ARIMA in capturing wheat price fluctuation. ARIMA struggled with high volatility and expected shifts. LSTM deep learning approach adapt better to market disruption. So we need for a policy application, government should integrate AI-based models for food prices forecasting. As a future work, we currently extend this work by working in the new paper. We segment the crisis and post-crisis period based on high and low variety to test multiple models. We add a third model, it's a profit model, to identify a robust model for seasonality and price fluctuation. For future work, we will explore hybrid model combining ARIMA and LSTM and maybe others model, expand forecasting for other essential commodities. As conclusion, accurate forecasting is critical for food security and smart city planning. LSTM perform better with a 97.5% accuracy, outperforms ARIMA with 77% accuracy. Deep learning method provide better long-term forecasting in volatile markets. Future research should integrate hybrid approach for optimal results. Thank you for your attention. And if you have any questions, please.
Thank you very much, Ahmed. Let's check the online attendees. Anyone has any question to the presenter? Okay, let's move to.
Thank you, Dr. Ahmed, for your very nice presentation. And I have one question. Is it something like curve fitting and any extrapolation algorithm can be useful for such kind of problems?
Yes, I think we use this forecasting as tool for policymaker and extrapolation. It will be useful for our work. This is a starting work, and we just explore two more famous model used and widely used now, but we need to explore more and to use hybrid models that prove a good result, and maybe also the interpolation will help to improve our results.
Okay. Also, you said about you used the historical data for wheat.
Yes.
Price. For how long the period you have used?
10 years. 10 years starting from 2014 to 2023.
طيب is climate change has no influence on the fluctuating the price as well?
Yes. Because there is many crises impacting in prices, and it's a very interesting thing to consider many others crises. But here we focus on the main things and political more because it's related to price and the exportation. But we can consider others, other crises related to other things, many other things.
Hope that your research will stabilize the price of wheat inshallah in the future.
inshallah. جزاك الله خيرا دكتور محمد خميس.
Dr. Muhammad, shukran, Ahmad. Now, let's move to the last and fourth paper by Sashini, Islam, and others, entitled Enhancing Solar Panel Efficiency Through Advanced Dust Detection, a comparative study of VGG16, VGG19, and Inception version 3 convolutional neural networks. The floor is yours, and please go ahead, Sashini.
Thank you, ma'am.
I think, need to stop sharing Ahmad's screen, and now you can. Now you are a host, and you can start sharing your screen, please.
Ma'am, is my screen visible? Hello, ma'am.
Do we hear
Yes.
you?
Yes.
Ma'am, my screen is visible?
Is visible. You can start, but just please use the show. Yes. Yes. Click slideshow. No, it disappeared now.
Ma'am, is my screen visible clearly?
No, it's not clear. You may need to stop sharing and share the whole screen maybe, and or share the right application.
Ma'am, is it visible now?
It is. Thank you.
Okay. Greetings, everyone. Today, I'm pleased to present our study on enhancing solar panel efficiency through advanced dust detection, a comparative study of VGG16, VGG19, and Inspection V3 conventional neural networks. My name is Sashini Islam, and I will walk you through our research findings and implications. These are our presentation outline. I will talk about them step by step. This is our background study, which includes solar panel efficiency significantly reduced by dust accumulation, obstructing sunlight, and reducing energy protection. Early defect detection is essential for ensuring the performance, reliability, and safety of photovoltaic, that is PV systems. While traditional methods face challenges, advancements in image processing and deep learning provide promising solutions in the long run. And these are the objectives for our paper, which includes to conduct a comparative analysis of dust detection models to enhance solar panel efficiency through automated dust detection, and to contribute a sustainable solar energy generation by integrating intelligent monitoring solutions. This is the impact of dust in solar PV. Dust accumulation severely impacts solar panel performance. A thick dust layer alters optical properties, increasing light reflection and absorption, thus reducing energy, the energy output. Studies show that a dust density of 4 grams per meter square and particle size range from 0.5 to 10 millimeter reduces the efficiency up to 40%, which is actually a huge amount. These are the model architecture we have used. Our model training involved we utilize 3 deep learning models such as VGG16 model architecture, VGG19 model architecture, and Inspection V3 model architecture to analyze and compare their performance in detecting dust on solar panels. Each model has a unique architecture optimized for image classification tasks. These are our training process. Our training process include pre-processing and augmenting images to 224 by 224 pixels using a batch size of 48. We fine-tune hyperparameters to enhance model accuracy and improve detection performance. This is our data set. Our data set consists of 700 images categorized into 2 classes, 285 clean panel images and 466 dusty panel images. The data set was split into training, testing, and validation. That sets to ensure robust model performance. This is our result analysis. We have divided here the distribution of a data set across training, testing, and validation phases. The majority of images are allocated of training, which includes 280 clean and 464 dust images for training, 111 clean and 180 dust images for testing, and 55 clean and 96 dust images for validations. This is our result analysis. This graph illustrates the training and validation accuracy of different modules, including VGG16 in figure 9, VGG19 training and validation accuracy for figure 10, and validation accuracy for inspection V3 training and validation accuracy and loss for figure 11. This is our result analysis. Which shows that the precision and recall F1 score for VGG16 are 96.5%, 95%, and 95.7%. And for VGG19, they are respectively 97.2%, 94%, and 95.6%. Lastly, for inspection V3, the precision rate is 98.3%, the recall rate is 97.5%, and for F1 score, it is 97.9%. And this is our result model. Comparing the accuracy and loss matrices across models, we can see variations in their performance. The result shows us different, the most effective model for dust detection in solar panels. In conclusion, our study highlights the effectiveness of deep learning models in dust detection. The integration of these models into solar energy monitoring system can facilitate early fault detection, preventing maintenance, and enhanced energy efficiency. Future work will focus on exploring more advanced deep learning techniques and developing real-time monitoring systems. Here are some key references that informed our studies. Thank you for your attention. I welcome any questions, and you can also reach me out via mail.
Thank you very much, Sashini.
Thank you.
Are there any questions for the presenter?
Question. Hello.
Hi.
Yeah. Thank you for your presentation. I'm much interested in
The time is
research. My question is that how or what is that?
Sorry, Mr. Shetul, I'm not hearing you properly. Can you please talk properly?
Oh, can you hear me now?
Sorry?
No, can
I'm
you hear
not
me?
getting.
Yeah. I say apart from the model that you mentioned,
Your voice is not clear.
Hello. We don't hear you, Shitu. We don't hear you well. Can you write your question on the chat?
Hello, can you hear me now?
Yes.
Hello.
Yes, I'm hearing you.
Okay, so let's take the question.
Hi, how's it going? Nice work. I just have a quick question. For the process you're doing, you're just identifying the amount of dust and the fault in the network. Is there any way to, in the process of cleaning the dust or anything, do you continue doing anything or any work related to this thing, or only the identification of amount of dust? Do you share
Sorry,
any?
can you?
Say it. Go ahead. Oh, what I'm trying to say.
Only for identification purpose.
Only
of
identification.
dust.
You identify the amount of dust or something like from the image?
Yeah, the amount of dust.
All right, that's it. And then what do you supply this to the main control of the boards or something? And then what does he do with that?
Actually, it affects the efficiency of a solar panel. Because whenever we use the dust detection in the solar panel, if dust is accumulated, then the efficiency is decreased.
Uh-huh. Got you. Got you. All right, I got it. Thank you so much. Good work.
Thank you. Thank you for your question.
You're welcome. Any more questions?
For the energy or the power to get better better performance, is it dust or also the angle of plate with sun ray? It's important as well as not the dust only. The angle.
Okay.
The angle and do you have something in order to maximize the energy gained from the solar cell? The angle with the sun ray, it's important as well, not only the dust.
Yes, sir. Sun ray is obviously important because it's basically a solar panel, and sun is the main source. Sun is the main source for working the solar panel. But dust detection minimizes the efficiency. If we implement a solar panel for a long term, then the efficiency reduces if the dust accumulation in that solar panel is increased.
Okay.
That's the main thing.
Thank you very much. Thank you.
Thank you, sir.
There is another question.
Is there any other questions?
Yes, a very quick one about the data itself. Which data did you use again? Or did you create this data your own or used one from Kaggle? The data you divided into testing and validation?
Own data, sir. Own data.
What did you say?
Own data.
Online data?
Collected personally.
Collected personally, that's what I'm asking. Okay, so you were gonna make it available somewhere or just purely for future work? Can people work on these things or it's strictly belong to you guys?
Sorry, can you repeat the question, please?
I mean, this data, will you put available?
Will available. It will available.
Will be available for future? All right.
Yeah, sure.
All right.
Thank you very much.
Thank you, sir.
Thank you very much, everyone. Thank you, Dr. Muhammad and everyone for enriching this session. And we can close now. Thank you very much.
Thank you.
Hello. Hello. Hello.